Earthquakes unleash unimaginable destruction in seconds. Despite centuries of study, their triggers remain mysterious. A new study offers clues to unraveling this enigma. Tectonic plates grind, building stress along fault lines. The trigger transforming stress into rupture remains elusive. New research reveals a mechanism in fault lines. Lab simulations show the interplay of movements and energy release. This discovery could improve earthquake prediction and warnings. While more research is needed, this is a significant leap forward. To unlock the secrets of earthquake ignition, researchers turned to a surprisingly simple material: plexiglass. While seemingly worlds apart from the immense forces at play within Earth's crust, plexiglass provides a valuable analog for studying the behavior of faults under stress. The team designed an ingenious experiment, carefully cutting sheets of plexiglass to represent the two sides of a strike-slip fault, much like California's infamous San Andreas Fault. By applying controlled shear force to these plexiglass plates, the scientists could mimic the slow build-up of stress that occurs along real fault lines. This controlled environment allowed the researchers to observe the intricate processes that unfold in the moments leading up to a simulated earthquake. By meticulously tracking the movement and interaction of the plexiglass plates, they hoped to gain insights into the hidden triggers that transform slow, creeping movements into sudden, violent ruptures. This elegant experimental setup, combining simplicity with scientific rigor, provided a powerful tool for peering into the heart of earthquake physics. By carefully observing the behavior of their plexiglass model, the researchers were poised to make groundbreaking discoveries about the nature of fault rupture. Central to this research is the concept of nucleation fronts, tiny cracks that act as precursors to larger fractures. These flaws dictate how and when a material will break. Previous studies identified these fronts as key in earthquakes. They move slowly, weakening the structure. The transition to rapid fractures was unclear. This study aimed to understand this transition. Analyzing these cracks could unlock earthquake secrets. The transition hinges on a balance of forces. This interplay holds the key to understanding earthquakes. Section 4. From creeping movement to seismic upheaval. The researchers discovered that the transition from slow aseismic creep to a sudden seismic rupture is not a simple, linear process. Instead, it involves a complex interplay of forces and a critical shift in the energy dynamics of the fault. Initially, as nucleation fronts propagate through the stressed plexiglass, they create a slowly expanding patch of microfractures. This expansion, however, remains relatively stable, with the energy required to break new material increasing in proportion to the size of the damaged zone. This phase, known as aseismic creep, can persist for long periods, releasing stress gradually without generating detectable seismic waves. The crucial turning point occurs when this expanding patch of microfractures breaches a critical threshold extending beyond a zone of inherent material strength. At this point, the energy required to break new material no longer increases proportionally to the size of the damaged zone. Instead, the system becomes unstable, with the release of energy exceeding the energy required for further crack propagation. This excess energy fuels a runaway process, driving the rapid, uncontrolled expansion of the rupture. The once slow and steady creep transforms into a cascade of failures, releasing the stored tectonic stress in a matter of seconds and generating the powerful seismic waves that characterize an earthquake. Section 5. Predicting the unpredictable, a glimmer of hope. The discovery of this hidden mechanism, this delicate dance between aseismic creep and seismic rupture, offers a tantalizing glimpse into the potential for earthquake prediction. By understanding the factors that govern this transition, scientists may one day be able to identify telltale warning signs of an impending quake. One promising avenue for future research lies in monitoring aseismic creep along known fault lines. While current instruments struggle to detect these subtle movements, advances in sensor technology and data analysis techniques could provide the sensitivity needed to track these critical changes in fault behavior. By combining real-time monitoring of aseismic creep with sophisticated computer models that incorporate the newly discovered mechanisms of rupture initiation, scientists may be able to develop more accurate and reliable earthquake forecasting tools. These tools could provide crucial early warnings, giving communities precious time to prepare and potentially saving countless lives. However, translating this fundamental research into practical earthquake prediction methods remains a formidable challenge. The Earth's crust is a vastly more complex and heterogeneous environment than a laboratory plexiglass model. Factors such as variations in rock type, fluid pressure, and fault geometry can all influence the rupture process, making it difficult to predict with certainty when and where a quake will strike. Section 6. Challenges and Future Horizons. While this groundbreaking research represents a significant leap forward in our understanding of earthquake ignition, it also highlights the immense challenges that lie ahead in the quest for reliable earthquake prediction. The Earth's crust is a complex and dynamic system, and replicating its full complexity in a laboratory setting remains an elusive goal. One major challenge lies in scaling up the findings from the controlled environment of the laboratory to the vast scale of real-world fault systems. The plexiglass model, while providing valuable insights into fundamental rupture mechanics, cannot fully capture the heterogeneity and variability of Earth's crust. Furthermore, the study focused primarily on the mechanical processes of rupture initiation, neglecting other potentially important factors such as fluid pressure and the influence of pre-existing fault structures. Future research will need to explore the interplay of these various factors to develop a more comprehensive understanding of earthquake triggering mechanisms. Despite these challenges, this research provides a vital stepping stone towards a future where earthquake prediction is no longer a distant dream, but a tangible reality. By continuing to unravel the complex interplay of forces that drive these powerful natural disasters, we can strive to mitigate their impact and build a safer, more resilient world. Section 7. A Deeper Understanding, a Safer Future. The quest to understand and predict earthquakes is a testament to humanity's enduring fascination with the natural world and our desire to mitigate the risks posed by its most powerful forces. This groundbreaking research, with its elegant experimental design and profound implications, exemplifies the power of scientific inquiry to illuminate the hidden workings of our planet. By peering into the microscopic world of nucleation fronts and unraveling the delicate energy balance that governs fault rupture, these scientists have not only deepened our understanding of earthquakes, but also opened up exciting new avenues for future research and technological innovation. While the dream of precise earthquake prediction remains a distant goal, each new discovery brings us one step closer to mitigating the devastating impacts of these natural disasters. Through continued scientific exploration and a commitment to translating fundamental knowledge into practical solutions, we can strive to create a safer and more resilient future for all.